Let us now study about hysteresis. Hysteresis means it's a phenomenon of lagging behind of the magnetic induction behind the magnetizing field. Okay, so we have to see this. Okay, B means the magnetic induction. Okay, H means the magnetizing field. Okay, so how to say this? Okay, how to say this thing? So first we have a coil here. Okay, and then in the coil we keep a substance, say a ferromagnetic substance. It can be iron. Okay, so what happens is we send a current into it. Okay, when you send a current here, a magnetizing field is created, H is created. Okay, and you also get a magnetic field, magnetic induction also. Okay, the B is equal to mu naught into H. Okay, mu naught into H, you can say. So by using this relation you can find the magnetic induction and magnetizing field also. Okay, so what we do is, we're not going to the experiment now. Okay, that you will see in college there. We will now see how the magnetic induction varies with the magnetizing field. Okay, it's not varying equally. Okay, let's see this now. So first let's start at this point here. Okay, let this point be A. Okay, from A what we do, we slowly increase the magnetizing field. Okay, this is the positive direction. Okay, so when you increase the magnetizing field, the magnetic induction doesn't vary directly. Okay, it's just like a curve only, like this way. Okay, and the magnetic field will increase up to some level only. Okay, afterwards you get a saturation. So at this point you get a saturation. Okay, so we got up to from here to here. So let me name this point as C. Okay, B is already written there, so we write a C here. Okay, so at this point C, what we get the saturation. Okay, so at this point C, you can see we get the saturation. Okay, magnetic saturation we get. Okay. Next what we do now, we have to reduce the magnetizing field. Okay, we are reducing H now. Okay, we are going this way. So when you reduce the magnetizing field, okay, the magnetic induction also will reduce. Okay, and then if you see, it doesn't come back again to you. Okay, it will come here. Okay, so this point is D. Okay, this point is D here. Okay, so this point D, I can say it as retentivity. Okay, from A to D, that means it holds a magnetic field. Okay, so point D we can also name it as retentivity. Okay, or remnants you can say. We'll come to it a little later. What is it? Okay, then again what we do, we increase the magnetic field in negative direction. Okay, we want to take all the magnetic field also, magnetic induction also. So we increase the magnetizing field in the negative direction, like this way. Okay, so at this point here, you can see at this point what happens, the magnetic induction becomes 0. Okay, so this point we name it as, say, E. Okay, so see this now, AE. Okay, this distance is called as coercivity. Okay, we'll come to definitions a little later. Coercivity. Okay, then what we do, we have to increase the magnetizing field in the negative direction this way. Okay, so as you increase it, it comes up to here. Okay, just like this, the opposite only. Okay, so at this point F, we get the magnetic saturation again. Okay, so this point F also is magnetic saturation. Okay, but negative direction gets saturated. Then what we do is slowly increase the magnetic field. Okay, magnetizing field, we increase it. So when you increase it, it comes like this way. Okay, and then let's name this point as same G. Okay, afterwards we have a G. Then next again we increase it. Okay, so it goes like this way, like this. So this point we name it as, say, K. Okay, like this way. Now you see this. So first what we had this point here. Okay, we start to increase the magnetizing field. So when you increase the magnetizing field, what happens? The magnetic induction also will increase. So we get the graph like this way. Okay, then what we do, we reduce the magnetizing field. Okay, so when we reduce it, the magnetic induction comes up to here. Okay, then we increase the magnetizing field in the negative direction. Okay, so it comes up to here. Okay, up to F we get. Then what we do, we increase the magnetizing field in the positive direction. Okay, so when you increase it, the magnetic induction goes like this way. Okay, so now you can see we have a curve like this way. Okay, or we get a loop like this way. This is called a hysteresis loop. Okay, that means, so whatever magnetizing field we get, the magnetic induction is not equal. Okay, it stores some magnetic field. Okay, some of the energy is stored there, And then you can notice that, okay, let's see, take these points here, AD, okay, AD, and the same way we have this distance also, that is equal to AG. Okay. This distance we say it as the retentivity or residual magnetism. Okay. The magnetism which is stored after taking out the magnetic field. So this is called as the residual magnetism. Residual magnetism. Then if you notice that this distance AE will be equal to AK. Okay, that's called as coercivity. Okay. So AE is equal to AK. That's also called as a coercivity. Okay. So it's let me know. So now this loop is called as a hysteresis loop. Okay, it's very, very important that we'll see the applications also a little later. Okay, now we'll go over definitions. Now we'll see what's meant by remnants or retentivity, and we'll see what's meant by coercivity. Okay. Okay, now let's study about remnants now. Okay, it's defined as the ability of the materials to retain the magnetism in them even after the magnetizing field disappears. Okay, so let's see the graph here now. See what we do, we increase the magnetic field like this way. Okay, this is the magnetizing field, we increase it. So first it went to C. Okay, then what we do, we decrease the magnetizing field. Okay, H means the magnetizing field. So when decrease it, what happens, it comes to D here. Okay, so actually it must come up to A only now. Okay, but doesn't do so. So it stores, there is some magnetic magnetism is stored here. Okay, that property is called as the remnants. Okay, or as you can say retentivity also. Okay, so even after the magnetic field is gone, okay, there is some magnetism stored there. Okay, we can take an iron nail. Okay, so when we keep in a magnetic field, after you take out the magnetic field also, it will become a magnet only. Okay, it stores some magnetism inside it. Okay, that is called as retentivity. Okay, next we'll see what's meant by coercivity. Now let us study what's meant by coercivity. The magnitude of the reverse magnetizing field for which the residual magnetism of the material vanishes is called as coercivity. Okay, so this thing you can understand if you see the graph clearly. Okay, see what happens is up to here we get retentivity, or you can say remnants there. Okay, we can see the iron nail has stored some magnetism property. Okay, but now we want to take it away. Okay, so what we do, we we bring the magnetizing field in the negative direction. Okay, so you see here we get minus H now. So as you bring it like that way, the magnetic induction drops to 0. Okay, so this thing, okay, this distance here, okay, that is will give us the value of minus H. You can see here minus H is there. Okay, so this magnitude of the reverse magnetizing field, okay, so we are reversing it. This is minus H here. Okay, for which the residual magnetism, that means this one, okay, it becomes 0. Okay, that means it vanishes, is called as coercivity. Okay, so we want to take out the magnetic property there. Okay, so that value of magnetizing field is called as the thing here, that is coercivity. Okay, then, okay, for example, see this was a coil there. Okay, and then in the coil we had this substance there. Okay, we send current like this way. So current is I. Okay, it produces a value H there. Okay, H is the magnetizing field. Now what we do, it got up to here. Okay, we must reverse it. So to reverse it, what we must do now, we send the current in the opposite direction. Okay, I'll draw another picture here. The same one only. Okay, the same substance here. But what we do, we send the current in the opposite direction. When you send current in the opposite direction, what happens? We'll get the minus H value. Okay, so that's how we get the minus H value. So that the magnetic property goes away. Okay, that value is called as, or this thing AE is called as the coercivity, the value of minus H. Okay, so it's just very simple only. Now let us see some more things there. Okay, let us now study about the next concept, that is hysteresis loss. Okay, so we see that when we apply the magnetic field, okay, current there, okay, we apply the current here, and then the magnetizing field will increase. Okay, and then we decrease it in the opposite direction that way. This whole cycle happens there. Okay, again we increase it, now it happens there. You see that in this stage, okay, we give some energy. Okay, some energy appears in the form of heat there. Okay, so that loss is called as hysteresis loss. Okay, because energy is lost in the form of heat. Okay, so there's energy loss there. Okay, so energy loss is in the form of heat there. Okay, energy is lost in the form of heat. Okay, why it happens is, You can see this is a molecular magnet, sir. Okay, inside the iron we have the molecules. We learn the domains and all. So these domains will be like this way. Then they will flip when you change the magnetizing field direction. Okay, so when it flips like this way, it will cause heat there. Okay, and this energy loss will be equal to the area of the loop here. Okay, area of the hysteresis loop. Okay, hysteresis loop. That means what? This one. Okay, this full area. Okay, we can take A, C, D, E, F, G, K, C. Okay, this full area will give us the area of the heat, or the value of the heat that is lost, or the energy which is lost there. Okay, so full energy will not be given there to substance. It will lose some energy in the form of heat there. Okay, due to the rotation of the molecular magnets. Okay.